All right, recording's resumed. Here's where we're gonna do this. I'm just gonna piggyback off his answer here because he went about this a little bit unique way. Let me just skip to the part that we actually care about on this one. Okay, right here back up a little bit here.
The change in rotational kinetic energy is greater for the disk. Now, you can probably easiest think about it is just think about it from the I omega. So we know the rotational kinetic energy is equal to 1/2 I omega squared, right? Now, probably the easiest way to describe, like the I omega is kind of the same, or I guess if they have the same angular momentum, you have to make an argument about. So if they both have the same angular momentum, then you have to make an argument as like, well, even the one has a bigger I. So we have to talk about how this guy has a larger rotational inertia in some sense because the mass is further away from the axis of rotation, because the same mass, but it's distributed further away from the axis. So we can say larger rotational inertia is going to mean that even though they have the same angular momentum, this guy is not going to be spinning at fast because their I omega should be the same. But because this guy has a larger I, he has a smaller omega. Okay, by that argument. Okay, so like, and then you can use this argument about the kinetic energy. Then you could say like, well, this is 1/2 I omega times omega, which is 1/2 times the angular momentum times omega. And so basically they have the same angular momentum, right? But this guy's moving faster. So the one that's moving faster is going to have more kinetic energy. So that's.
All right. All right, let me switch back over here. Okay, yeah, where it is. All right, so yeah, that was a little bit creative way to do this. Right, so here, just focus on this term because this is what we're trying to compare for the two disks. Right, now this is generally true for each disk, but 1/2 I omega squared is that 1/2 times IA times omega, and then this part you can bracket off and say, well, that's the same for both. We already established that, right? So we established that right here. Angular momentum is the same for both. Right? That's what I omega is. Right? L equals I omega. Right? That's the part I just bracketed right there, right? Okay. Right. So L is the same for both, but remember, the disk is spinning faster and the hoop is spinning slower because the hoop has more rotational inertia. They have different I values. They have different omegas. I times omega is the same. So the fact that the hoop is spinning slower means it has less rotational kinetic energy. So the disk must always have more rotational kinetic energy. Okay, you guys got that? Right. That was a pretty tough one. Okay. That'd be a good explanation there. Okay, and finally, number 5. Okay, last one, 7 points. We got rod, sphere, rod with a sphere attached to the end. Is connected to a horizontal mounted axle, carefully balanced so that it is rests in a position vertically upward from the axle. Center of mass of the rod sphere system indicated with that X symbol, that circled X. The sphere is lightly tapped so that rotates clockwise with negligible friction. Okay, so it goes from figure A to figure E, frame A to frame E. You can see, right? Take some pictures. Student takes a video. And we'd see these 5 frames. Okay, there we go. So it was just barely balanced there. You give it a light tap, point, it goes 0 point. Okay. And the center mass of that system is designated with that circled X. Use the frames of the video to answer these questions. Which frame is the angular acceleration the greatest? Justify your answer. Angular acceleration. Guys, is torque equal to I times alpha? So alpha. Guys, everybody look up here. I'm trying to help you out. Torque divided by I. Is that true? Isn't this Newton's second law of motion, but in a rotational context? So if you want to maximize alpha, right? See, like I is the same no matter what. I is just how the mass is distributed. That's the same for all 5 frames. I is the same for all 5 frames. Right? But torque, torque is R cross F. And F is provided by, well, something to do with the weight, right? Now, this is a cross product, so I only care about the perpendicular components. So here's what I'm thinking. I'm thinking that in frames A and E, it's kind of like opening a door, or trying to open a door, but you're pushing parallel to the door, right? It's never going to turn the door. But look at frame C. Isn't the force perpendicular to the lever arm? Isn't that going to maximize your torque, which is therefore going to maximize your angular acceleration? Frame C. Okay, you guys got frame C? In which frame is the rotational kinetic energy of the system the greatest? Okay, so the torque and the angular acceleration is greatest frame C. But what about rotational kinetic energy? Well, kinetic energy, guys, guys, everybody look up here. I'm trying to help you out. Right? Isn't the energy of the of this whole system plus the Earth, if you include the Earth in the system, conserved? Isn't it all potential energy up here, right? And then that potential energy is converting into kinetic energy down here. Wouldn't frame E be the maximum kinetic energy? Frame E is maximum kinetic energy. Okay, you guys got that? All right, which is exactly what they're showing this figure. It's frame E. The rod sphere system has mass m, length L, and okay, so the center mass is at 3/4 of L. Let's show figure 3. Derive an expression for the change in kinetic energy of the rod sphere Earth system from the moment shown in frame A to frame E. So we're going from frame A to frame E, and we're looking for the change in kinetic energy. Well, there was 0 kinetic energy in A, and it's probably all kinetic energy in frame E. Hey, is that gain in kinetic energy the same as the loss in potential energy? Right? Okay, so start from there. I'm going to say sum of energy initial equals sum of energy final. It starts off as all potential energy and ends up as all kinetic. Okay, so we're doing the mass of the system times gravity field times the height goes to we're solving for changing kinetic energy. Well, I'll just call this delta K because it starts off from 0 anyway, right? Okay. Now, one more thing. The height change. Look at this height right here. Right? If this went from up here down here, do you guys see a total height change of this 3/4 L plus this 3/4 L? You guys see that? 3/4 plus the 3/4. Right. So this is I should have done capital M because they went with capital M. Right, guys. This was 3/4 L plus 3/4 L is your change in kinetic energy. Right, and that's like 3/2 L. You put it all together, and we're looking at 3/2 mgl. Okay, that's what they were looking for. Right, you guys go there. Right, any question? All right, briefly explain why the rod and sphere gain kinetic energy even if the Earth is not included in the system. Okay, so guys, if the Earth is not included in the system, are you allowed to consider potential energy mgh? No, right? Would this be at that point an open or closed system if you do not include the Earth? It'd be open. There is an external force now, right? So like when you included the Earth, the gravity force was that mg was internal to the system. It was the Earth and the sphere pulling against each other, right? But if we throw the Earth out, now that force it's still there. It's just an external force now. Okay, so you could compare the speed of the sphere to a nearby object in the room and say the speed of the sphere is still increasing. Okay, the fact that the speed of the sphere is still increasing means that there's a change in kinetic energy, right? Is provided by, in this case, an external force. So the mechanical energy of this open system is now increasing. Okay, all right, ever got that? Right, a question. Okay, that we did cover them all. We covered them all. All right, so everybody good with those? All right, good deal. All right, so let's call that a wrap on today.